Now you can
Professor,
probably hear me.
yeah, we can hear you now.
Yeah, sorry. I had physically shut the mic off, not only unmuted. Thanks for letting me know. All right. So yeah, everybody, yeah, is finished with the quiz now. So like I said, take this time while we have our second remote session to go ahead and answer any questions you have about anything that came up in the other lab with Quartus, right? Anything, questions related to this lab, right, or the pre-lab. So does anybody have any questions?
So far, so good.
So far, so okay, that's good. That's good. Yeah,
How
go ahead.
how do you want the lab report written? Do you want it on Word or you want us to handwrite it and create a PDF?
You never handwrite any engineering reports. Well, any formal class lab reports you never handwrite. So those all have to be typed. You can use you can submit a PDF if you want, or you can submit it in a Word doc form. Either way.
So what I understood is that the lab report, you want us to add the simulation that we did for all those circuits. Do you just want us to then just copy and paste those in whatever Word that we want to submit that in and add that word to the compressed folder that we're going to be submitting for all the lab assignments?
So yes, right. So yeah, in this lab, you are going to right. You started with circuit A, and in this lab, you're going to go ahead and draw two other circuits, the canonical product of sums, the canonical sum of products. And then you're going to run a simulation to show that all three of those circuits produce the same output. Right. So in your lab report, you definitely want the simulation. You want pictures of your circuits. You want your truth table. So that will all go in your lab report. And I've also given you a set of guidelines for your lab reports and an example lab report. If I can bring that up on Quartus, but yeah, so you will go ahead and submit that. It's easiest if you just put it in that compressed folder. So when I open it up, I can read that and go through your files as well. Let's see, you go to the assignment.
Thank you.
You're welcome. Okay, Matthew. No, we're not writing Verilog code for this file, so there shouldn't be a Verilog section. I know you're just trying to cover all your bases, but in the next lab, you will write Verilog, right? So yeah, if most of our labs after this will do, we'll be writing everything in Verilog. We'll do a few things symbolically and schematically as the semester goes along, but for the most part, we'll write everything in Verilog. So, and then typically when you'll put your Verilog code, that typically goes in an appendix, right? Not in the main body of the report. Same way, if you get, as we go along in the lab and we start, we have truth tables, things like that, you can choose to put them either in the main body of the report, or you could put them in an appendix, as long as when you're writing your report, you say, oh, well, the truth table for this circuit is found in Appendix A. If you don't want to crowd the main body of your report with some of that, that's fine, as long as you reference where things are. Okay, so I'm going to take these questions in order. All right, can I go over how to fill out the truth table on problem 2 in the pre-lab? Yes, I can. Do that in a second. And I'm going to take the easier question. If you multiply A prime and A prime, will that just simplify to A prime? So yeah, if you so next week's lab and pre-lab are already up, where we start talking about Boolean algebra. So there is a Boolean algebra law that says, right, X ended with X always produces X. So A complement and with A complement will simplify to A complement. But so problem, all right, let me bring up the pre-lab. Actually, let me actually bring up that circuit in the lab form so it's easier to read. Go to those files. I don't know why Quartus has decided sometimes it links out to their website. It seems to like to link out to their website and take forever to come up for me. All right. Bring that up. And let me grab the pre-lab. Okay. Looking to see if I had a nice form already started. Got a function of A, B, F is function of A, B, C, and D. Right. So in terms of coming up with, right, the formula for F, I start typically here at the left-hand side of, or the lowest possible level of our circuit. So over here on the left, the way I've drawn everything. And we start looking, I'm gonna start here. Actually, really help if I bring up and insert a new page here. So let me save this. Let's just start writing out the equation. Put a page break where I don't want it. I go down here. Play. Go here. All right, so our equation is going to be, and let me make this text bigger. F is a function of A, B, C, and D. Right. And that came from, right, the output pin was named F, the inputs are named A, B, C, and D. And let me get both of these maybe on the screen at the same time. Let's go here. Yep, this is much easier to do on the whiteboard. All right, so this term right here, right, is going to be C ORed with D. That's going to flow into another OR gate, which is going to be ORed with these terms here. So we've also got, then that's going to be ORed with this combination of here A and it would be not. So A, B not. And this term is ANDed with this term here, which is A not and with B not. So we've got A not and with B not, right? Here's this AND gate here. There's ANDing these two together, right? This whole term here, right? If I try to put parentheses around things, that then is ORed with this term. Again, if I put a square bracket here, and that gives us the input to this OR gate, right? And then if we continue on this level, this whole term then eventually will be flow into this AND gate. And so we've got one term in that relationship here, right? Now we can go ahead and write the equation for this term. So that's going to be AND with, right, A ORed with C naught. If you see me making a mistake, holler, because once in a while I accidentally drop a complement, or I get talking and don't type what I'm thinking, or I just plain make mistakes. All right, so there's that term, and that's then going to be ANDed with this term here, which is A, right, ORed with B, ORed with C naught. Right. That's that AND gate there. So now we have this relation here, which we start getting a lot of parentheses, which this is written in such a convoluted fashion that hopefully as we work with standardized forms, you'll begin to appreciate having the same standardization all the time. We won't write functions that look like this because they're hard to follow and they use way too many gates and inputs. All right, so now we've got this other AND gate out here, right? It needs to have then these terms flowing into it. And we have to consider that this AND relationship we just wrote here is going to flow into another AND gate there. All right. And so I can end up ANDing it with the output of this. I was trying to see if I need to put an OR in between or anything. I don't. So out here then, we'll form this group. Right. So this group for this AND gate is going to be, this is an OR gate. Again, we go with square parentheses and let's go with A naught, a complement, OR with B, OR with C naught, OR with D naught. There's that term, which is now going to be ANDed with this term, which is B naught, ORed with C, ORed with D naught. So this term is this term ORed with this term ORed with this term. This is this AND gate. We've got that AND gate up above. So they then flow into this other AND gate. So we've got this being ANDed with this. Finally, that produces F. So this is our equation that we're working with.
Professor, I think the second term should be a plus. So it's because it's an OR gate. So C plus D plus A B prime. So it should be A plus B prime because it's an OR
Oh,
gate.
yeah, it is. Thank you. Yes. Correct. These were OR gates. Yep. Thank you. Throw the whole thing off. All right. You are correct. All right. Thank you very much. That should be ended with that. That's over that. All right. All right. So when we fill out our truth table, I'm going to grab this and throw it here. Move things onto the screen. Image. I want it to be an object. Just give me text. Oh. Oh. And it left some of the LaTeX things in there, which is annoying. Really annoying. I want the LaTeX in there. Keep the source formatting. You can match the destination format. Okay, fine. Leave it like this. Usually don't work this way. Yeah. All right. All right. What I'm trying to get to is that you could solve these terms individually. Right. Come up with your final truth table in terms of, I could start, let me make the text much bigger. These are our 4 inputs here. Which we know we have our unique binary combinations. So we have these 16 unique binary combinations. I said, we could start filling this out in intermediate form. The other thing we can think about is the fact that these 2 terms are going to be ANDed together. So let me see if I could just grab. Work with the A naught, or with B, or with C naught, or with D naught term. That's going to eventually be ANDed with So I'm working with these terms out here on the right. B naught ORed with C, ORed with D naught. All right. We're trying to get the F, eventually our output F. Come up with our zeros and ones. Some sort of intermediate terms. Like I said, we could go through the different combinations and fill this in the long way, but what I like to do is I like to think about, well, if this is an and relationship here, like this term is going to be anded with this term. We know then that both of these terms would have to have a value of 1 in order to produce a 1 of their anding. And if either one of these terms have a value of 0, because this whole expression here is going to be anded with this whole expression here. Like I said, if either this term, right, or this term produces a 0, the entire thing will be a 0, which then it won't make any difference what any of these terms are here, right, in terms of our final and with F. So one quicker way to do this is we could go ahead and try to figure out, use a smaller term to say, well, where could this produce a 0? For what values? For what input values might this produce a 0? Right. And with an OR gate, right, these inputs for the max, right, this is sort of a max term sort of form, or it's a sum form. So it's an OR gate form. In order to produce a 0 out of an OR gate, all of our inputs to our OR gate have to be a 0. But now we're looking at the point where we've got B complement, D complement, we've got C. And for those of you that are newer to this, you're just now in 1510. Probably can't look at this just as easily. So if I were to just go here, B complement, C, D complement. Right. So here in our input in these particular rows, B is a 0. So B complement is going to be a 1. In these first 4 cases. It doesn't matter then, in order to determine our output here of B naught ORed with C or with D naught, does it really matter what values we have for C and D naught?
No.
No. All right. So we know in this case, this would be a 1, this would be a 1, this would be a 1, this would be a 1. All right. So we don't care about that. Now, everywhere that and B is a 1 here, well, now we have to consider, right, that would make these all zeros. That means we need to consider then other values here. Like, and then in these 2 rows, in these 2 cases, C is a 0. Right? That means we need to consider what the value of D naught would be. Right? So D in this row is a 0, D naught would be a 1. That means we're going to end up with a 1 here. In this row, D is a 1, so D naught would be a 0. So there we've got a 0 in our OR gate output. Right here, where C is a 1, we don't really care now what D naught is because we know that this result is going to generate a 1. All right, again, B is going to be 0 in all of these cases, meaning, right, it's a 1. Here, that means our OR gate output will be a 1 here. Again, we have the case, right, basically go through a similar set of cases here, right? again, C is a 0 in these cases, right? D naught, then because D is a 0 here, D is going to be a 1 here, D is going to be a 0 here. Again, because D is a 1 here, we get a 1 here, we get a 0 here. Right. And then same thing here, where C is a 1. In both of these cases, we know that this output has to be a 1, right, which then gives us the value, at least of this expression right here. So all we really can determine about F at this point is any place where, because this expression is going to be ANDed with this. Then maybe make it a little bit more clear. A naught ordered with B, ordered with C naught, ordered with D naught. Right. In this case here, right, where one of these, where this one's the 0, it doesn't matter. So when we say it doesn't matter, we don't care what this is. A lot of times we use an X for like a don't care. X means we don't care what that term is, because now if we know if we AND this with this, well, we've already got a 0 here. We know that F is going to be 0 because this whole result then is ANDed with this whole result, meaning we don't care what is in these other terms, at least in these two cases. We know that F must be a 0 here. And then we can go through and we can figure out, well, what would be the value of A naught ordered with B ordered with C naught in these cases where we have ones here. And anywhere we get the zeros, we could fill in a 0 for F. Then we have to do something similar, right, with these other cases over here as well. And I lost my, trying to figure out where my one, oh, canvas menu's gone to. All right. All right. So Kenny, does that help answer your question on how to fill out that truth table in problem 2?
Yeah, originally I was going to do it in a very complicated way, but it seems like you really streamlined it.
Okay, good. Yeah, if, like I said, as a newer beginning student, I had exercises like this in 1510 where we'd have to fill out a column for each one of these. But yeah, after working with it, like I always try to look for shortcuts that don't get me into trouble. And one of those shortcuts is I know if I'm ANDing things together at the end, I figure out, oh, in what cases will any of these inputs be a 0, so I can start ruling things out. Okay, good. All right, that was a good question. Sorry for the long, tedious answer with Excel and Word. All right, other questions? And of course, then you can always check your truth table today or what you came up with in your truth table, right? I did give you this circuit, right? Which then when you run your simulation, you don't have to draw the circuit. I gave it to you, so you can include that in your lab. You can run a functional simulation and that will show you where the 0s and 1s are, and you can check that against the truth table you came up with. Other questions? Is that for this particular lab, right? Introducing block diagrams, the idea of, block symbols, right? Because eventually we will be making circuits. Let's see, lab 3, we're not necessarily going to make a circuit we're going to reuse. In lab 4, we'll start making circuits that we have to use in more than one place in our lab. So I want to start introducing the idea of block symbols now. Right. So that, right, when we draw things schematically, we can create these block symbols if you followed that tutorial. And then right? We don't have to keep redrawing things in our circuit. Like when we start creating circuits that are called multiplexers and decoders and adders, we're going to want to use that. Some of those circuits we'll use in more than one lab. So you don't want to have to, we'll actually end up writing those in Verilog, but you can port your Verilog code from one place to another. But even if we drew them schematically, right, the idea is that you draw the schematic once, you create a block symbol for it, which is sort of this black box abstract representation of the circuit. Meaning if you just see a symbol called circuit A here, right, and we tell you, you have to tell the user, right, whoever's going to use your circuit, you have to either give them a circuit equation, or when we work with things that are like multiplexers, full adders, decoders, we'll know, oh, well, this is what a decoder does, or this is what the adder does. In other words, you have to tell your user something about your circuit. In this case, if we went ahead and gave the user either a truth table or we gave them a canonical expression, right, they would know what the output F should be based on the inputs A, B, C, and D. What you'll do with this lab, right, is you're going to implement the circuit in these standard forms, these canonical forms. So canonical means that we don't reduce, we don't simplify the circuit. In next week's lab, you're actually going to take the canonical forms and find the minimized the minimized sum of products and minimized product of sums forms, because right, we typically want to minimize our circuits to reduce the number of resources that we use in them. Like I said, today, the point of today is all three of these will work the same. You just have this abstract block symbol. You don't need to know how this was implemented underneath. You don't need to know really how ugly circuit A is if you just gave somebody this symbol, right, to use. And then in next week's lab, you will actually write a Verilog implementation using Verilog gate primitives, and we'll do the equivalent of a schematic symbol where we'll instantiate the Verilog module, and you'll begin to learn how to use your same Verilog code over and over without having to rewrite the code. All right. So if there are no other questions, I will let you get working on the lab. And I will just hang around Zoom. If you have a question, you want to pipe in with a question, if you're having any issues, just I'll be hanging out to answer them.